Hello, I'm Umnik. I will solve today's second division to the first round, and I'll try to explain what I'm doing. Problem A. Have an array and to find three numbers that their sum is odd. Okay. Well, sure. So we can either take three odd numbers or one odd number and two even numbers. So let's just read everything, sort the numbers into even and odd, and check if we can do one of those two things. So I want to get two vectors, indices of odd numbers and indices of even numbers, and we can do it like this. Take the parity of our number, and just in vector with this ID we will push index of this number. And now if we have at least three odd numbers, we can just take them. And print yes and three indexes. Otherwise, if we have at least one odd number and at least two even numbers, we can take them. Otherwise, the answer is no. And here we should print like this. I checked if we have to print them in increasing order, and no, we don't have to do that. And also, yes, the indices should be distinct, but if I'm not mistaken, this is the only place where they say it, which is not cool. I mean, you can guess that they should be distinct by the fact that n is at least 3, but like in the problem description it is not said that we should use 3 distinct elements of the array. So like this is not the whole problem, which is, well, it's fine, but I think it's not okay to put it only in the output description and like in not a prominent way. Like you can not see it. That's not okay. Problem B. Have an array. Split the array into k at least 2 subsegments. Split means like everything should be in one of the segments. Yes. And calculate the sum in each of the subsegments, and then take GCD. We want to maximize this GCD. Okay, so we can see that if we have some way to split our array into subsegments and we have more than 2 subsegments, we can merge, for example, 2 first subsegments. So we will remove 2 numbers and insert their sum. I state that if some number divided all the numbers, then also it divided sums of some of those numbers. I mean, for any subset of these numbers, its sum is also divisible by that number. So that change cannot decrease GCD. So in the optimal solution, in the optimal way to split the array, there will be exactly 2 segments. Or like there is an optimal solution that splits the array into 2 segments. There are only like n-1 of such splits, so we can just try all of them, calculate GCD, and take the maximum one. And I think you cannot do much better than that. Like, you can probably say something smart, like we are actually choosing the points where to like put borders between segments, and it can be shown that well, the sum on the segment is difference between prefix sums in the borders. And I want to say that GCD of sums on segment will be equal to GCD of all prefix sums in borders. Because like you can like GCD of x and y is equal to GCD of x and x plus y. So when we have like some segments, we can, instead of second segment, second segment, we can take sum on first and second segment. That will be prefix up to second border, then prefix up to third border, and so on. And so like we have to take 0 and the sum of whole array, and then we have to choose at least one number inside, like prefix sum that is not the first one or the last one. Obviously we'll choose just one, so the problem can be reformulated as well, prefix sum in the beginning is 0, so we don't care about it. So we have a number that is sum of all array, and we have a set of numbers. We need to choose one number that maximizes GCD with our fixed given number. But I don't think that it can be solved much better than just trying all of the options. I don't see it. Like, we can factorize the given number, but I don't think that gives us any profit. That's not what I want. But this problem would be solvable if they said, like, you have to choose at least, you have to have at least like 10 segments. Then we could, we know that the answer is always a divisor of the sum of the whole array, so we can just try all its divisors, and for each divisor check how many other prefix sums are divisible by it, and we can, if we can choose 9 of them to get like 10 segments, then this is a good option. We should update the answer. So the solution would work in n times number of divisors plus time needed to factorize. Time needed to factorize, let's say, square root of sum. So it's square root of n times c, where c is maximum element, but it's still fine. Like, and the number of divisors is bounded by something. Well, for 10 to the 13th, I don't know, like probably 10,000 maybe divisors, but like it's a solution that would work in some reasonable time, and like it wouldn't be possible like this, just checking all the options, because there will be like n to the 9th power of them. So that would be a more interesting problem, but it wouldn't be a second division B. So now I want to check all the splits. I will maintain sum on prefix and suffix. That's L and R. I already calculated the sum of all the numbers in the array, and now I will move the border and increase sum on prefix while decreasing sum on suffix, and then updating the answer with GCD. There should be built-in GCD function. But something doesn't work because I should iterate up to n-1 here. Like, I cannot take the whole array into prefix and leave empty suffix. Problem C, have n guests and m tables. For each guest we know which type of dish they want, and for each table we have maximum number of people that can be seated at the table, and for each table we have to serve the same type of dish to this table. Find the maximum number of satisfied guests that can be obtained by optimally choosing the type of meal for each table and assigning guests to tables. So like we have to split our n numbers. We have n numbers, we have to split them in some groups. Then for each group we have to assign a table of size, at least the size of this group, and we will then choose like for each group the number that is satisfied, and like all of the numbers that are equal to that one in this group will be satisfied. This sounds like some kind of knapsack, but I didn't get what to do right away. Maybe I misunderstood the problem. This looks and be hard. Like for each meal, for each type of meal, we can calculate the number of people who likes it. Then, like we can uninvite some people if we will not satisfy them. Like why even bring them here? And all the remaining people should be satisfied, so we should assign some subset of tables to each group, so that total size of those tables is at least the size of the group. But like even checking that it's possible to satisfy all of them sounds and be hard. That's just it looks like a very general knapsack. I mean, our numbers are small, but we have a lot of groups. And 2000 sounds big enough so that like no square root type of shit can pass. Like, yeah, we will have some small number of different numbers, but let's just say that sum of ci is equal to n. We have only 3 types of dishes, so like for each type of dish we know the number of people that like it. Then we want to check if it is possible to split the set of this ci numbers into 3 groups with given sums. That doesn't sound like a problem that can be solved in like polynomial time if we change 3 to like something, some k. I even think that like there is something very similar in Timus, and like it's also impeccably like that. It's known that it's just some shitty contest from 20 years ago, which like the intended solution is some greedy, which is incorrect. They just left it as is. What? Like, okay, let's read it again. Yeah, I think I understood the problem correctly. And like there are no questions and 500 people solved it. Yeah, but yeah, a lot of smart people just skipped problem C. How is the coordinator of this? Cool. Test. Come on. Let's skip problem C. Problem D is interactive. Okay, in problem D, there is a hidden number n. We can do queries. Like in the beginning, we are given like pop count. I guess number of unit bits. It means like 1 bits, right? Yeah. And we have to guess the number using basically log operations. Like we know that n is up to 10 to the 9th. Our query is number x that should be at most n, but we don't know n, and then x will be subtracted from n, and we will receive new pop count. And we need to guess the original number n, and we cannot do queries that will make n negative. Okay, that sounds pretty simple. Like we should just guess the position of all 1 bits. So if so let's say that our hidden number is something like this. Let's ask to subtract 1 from it. What will happen? We will look at the rightmost one in the number. So everything here will remain as it was, but here we will get 0, 1, 1. And so, like, how did pop count change? We decreased it by 1 here, but increased it by this length. So by looking at the difference of pop counts for these two numbers, we can understand what was the position of the lowest 1 bit. Okay, now we can mentally subtract it, and so we're like doing the same thing but starting with 0 here. again asking 1, we will find the position of this bit. How do we actually do it? Like we have to actually make some query, but like we know the position of that bit, we subtracted 1 in the previous operation. Well, okay, let's subtract this thing. 2 to the power of position of this bit. Then we will subtract like this bit and 1 more from the previous operation. And then again, like we can find the position of this bit and continue until we found CNT bits. We were given pop count in the beginning, so when we repeat this for pop count times, we just stop and print the answer. And that works in pop count queries, so it's even like 29 actually, because like the smallest number with pop count 30 is 2 to the power 30 minus 1, but that's greater than 10 to the 9th. No comments. Okay, guys. See you this. Well, I hope I'm wrong and they actually solved it or something, or like I don't know, the solution is just some fast brute force, or I don't know. I don't know how one can solve this problem. It looks it doesn't look possible. So this is multi-test. In the first query, I should ask to subtract 1, and then I should ask to subtract 2 to the power of previous bit. So if I first set it to 0, then it will be correct for the first query, and now each time I will set it to the next bit. And you shouldn't write code like that, but this thing means that we will repeat this operation k times, and like you should that's okay by my standards, but you shouldn't use the value of k after that. But like I can understand that it decreases by 1 each time, and so then some answer will be returned. I can just scan last. And I think this is the correct position. Like after I decreased k by 1, that's like the number of bits not including the one I removed. So pop count minus k will be the number of ones on the suffix that were like new ones. So the position of the bit I removed is Alright, the position is no, right, if there is like 1, the position is 1. Don't forget to flash output. Problem E, we have huge graph. Huge complete graph. So 10 to the 18th vertices. The weight of an edge between two different vertices is GCD. Then we remove some subsegment of vertices, and now wondering how many different weights are there and different weights. So the graph is not needed. It's just like we have numbers from 1 to L-1 and from R+1 to 10 to the 18th. Oh no, the other way around. So, okay, how many different GCDs we can get if we take two numbers between L and R? L is up to 10 to the 9th for some reason. Okay. So it has nothing to do with the graph. We are just interested. Calculate number of positive G such that there exist two numbers x and y such that they are on given segment and their GCD is equal to G. For fixed G, both of those numbers should be divisible by G. Let's first of all, on the segment there should be two numbers divisible by G, and I state that that's enough. If there are two numbers that are divisible by G, then we can find two numbers whose GCD is equal to G, and the reason for that is just we can take two consecutive numbers that are divisible by G, then if they're equal to G times K and G times K plus 1, then their GCD is equal to G times GCD K and K plus 1, which is 1. And in general, in such problems, as in problem B, it can be useful to, like when we want to calculate GCD of some numbers, it can be useful to substitute one of them with their sum or difference. Here, like difference is G, so we are taking GCD of G and something that is divisible by G, that is obviously G. So we just need to calculate the number of integers such that there are at least 2 of them on this segment. Okay, so the length of this segment is r minus l plus 1, and if 2g is at most length, then surely there are at least 2 numbers. Why? Because there is exactly one number divisible by g in any g consecutive numbers. So we can take like 2 segments of length g side by side. It will fit in our segment, and in each of them there is exactly one number that is divisible by g. If g is strictly greater than len, then it is impossible, because even if g is at least len, but I think it will be easier to implement if we say strictly here, because between 2 numbers that are divisible by g, there should be distance at least g, and we cannot fit 2 of them if it's short. So so for g that are at most 1 over 2, the answer is yes. We just need to add this to answer. So what we want to do is we want to check for numbers from this one to len inclusive. And what I want to state, like we cannot fit 2 whole segments, right? So we cannot have 3 occurrences of numbers that are divisible by g for given g from this segment. But we know that there is at least 1 occurrence, because we can fit 1 segment of length g. So the number of g such that there are at least 2 occurrences from the segment is the same as exactly 2 occurrences, and it is just total number of occurrences of like sum of number of occurrences for all the numbers from this segment minus the number on this, of the segment, the length of the segment, because we can only have either 1 or 2 occurrences. We want to calculate those with 2 occurrences, so we calculate their sum and then subtract 1 for each of them. Okay, so it's easy to calculate the length. Now we want to calculate total number of occurrences here, but that should be easy. Like how to calculate number of occurrences for a given g. Well, the number of numbers that are divisible by g on prefix from 1 to r inclusive is just r divided by g rounded down. But we have to remove those that are smaller than l. But that's like the number of integers that are divisible by g strictly smaller than l, or like not strictly smaller than l minus 1. which we already know how to calculate. So this is number of occurrences, and now we have to calculate sum of these things. Over G in this given segment. We will separately calculate this and this. And that should be done by some kind of square root thing, but our numbers are big, so we have to use that L is kind of small. So yeah, if this segment, so if the length of our segment is big, for example, like bigger than 10 to the 10th power, then it means that left border of the segment is like greater than length over 2, which is at least 5 times 10 to the 9th. So this thing is always 0 because L is small, and so it should be easy to calculate. We are interested in number of numbers that like for which 2G is at most R, but that's just error word. So yeah, if R is at least like 10 to the 10th, then the answer is just that. Otherwise, those numbers are up to 10 to the 10th, and we can calculate this thing in square root time by saying that either G is small, like up to square root, or this thing is small and we can iterate over it instead. That's like standard thing. That's cool. Like creative use of additional limitation, additional constraint. So we are interested in those sums for numbers between ln divided by 2 not inclusive and ln. It doesn't matter inclusive or not. So instead we will write a function that calculates it for numbers just up to some border, and we will take differences in space. Basically, we want summon some segment, we write it as difference of two prefix sums. As we already did with this segment, we can also do it with segment of numbers over which we want to calculate the sum. And so yeah. So we will write a function that calculates the number of numbers, the sum of floor of r divided by x for x from 1 to the given parameter, and we will take difference of those things in these two borders and do the same thing for L. So it is kind of similar to like 2D prefix sums, but we can like if we know 2D prefix sums, how to calculate the sum on rectangle, and we need to subtract like len minus ln over 2 plus 1. I want to say no, not plus 1, just that's the length of the segment on which we calculate. That's the answer. So now we want to calculate sum from 1 to r of floor of a divided by x. And we want to do it in square root of a time inclusive okay, I want not inclusive. And now we will iterate first over this value, and we will find the range of values of x such that, let's call it d, such that this thing is equal to d. So we want a over x to be equal to d, which means that x times d is at most a, but a is strictly smaller than d plus 1 times x. So this means that x is at most a divided by d, and we can take integer part. This part means that x is greater than a divided by d plus 1. Strictly greater. So this actually means that we can take also take the whole part here. I'll take floor, because like x should be integer, and so to be strictly bigger than some real number means that it is strictly bigger than its integer part. So I guess I shouldn't have done that. Okay, so x is between this non-inclusive and this inclusive. So our borders are this and this. But we are only interested in numbers that are up to small r. So if all the numbers that we are interested in are to the left of our half interval, we don't do anything. Otherwise, we want to add to the answer what? The sum of a divided by x floor over these numbers, but each of them is equal to d, because that's what we wanted, and their number is what? Let's say the distance from right border to left border. I should have put like whatever. Okay, and now after that we have already calculated the sum for some big values of x. We do not want to count them twice, so we will say that from now on we're only interested in numbers that are up to L, because for bigger numbers we already calculated. And this way we will traverse like corresponding x's in decreasing order, so everything will be calculated. But this cycle works in linear of a time. Well, now it can't stop, so it works in infinite time. It's an infinite loop. So we want to write some stopping condition. What's the stopping condition? When this r is small enough that we can just iterate over all the x's, and we can say that we will stop if d becomes greater than r. We already spent this much time. We can spend it again in this simple for. It will not change the complexity, and the complexity is actually square root of a, because like we can see that after when d becomes greater than square root of a, r will be at most square root of a, so we will stop somewhere around there, and like you don't have to actually like write down bounds accurately, just write it like that, and it's simple. And like some people use binary search to find those borders. You don't need it. And well, actually it can be done even simpler than that, but like that's the most verbose way to write it, like in the simplest way, I think. The simplest way known to me. So okay, this function works in square root of a time, and yeah, also I want to say that for numbers that are bigger than a, this is 0, so we can ignore them. So here we can write R is minimum of R and A, and now we don't need this because like we know that these segments will cover all the numbers from 1 to A, and we will like start from the bigger ones, so this minimum is always equal to small r. And so we don't even have to calculate this big R, which kind of makes sense. Like we calculated it on the previous iteration as L. Like why would we do it again? So yeah, this is a very fast square root. We will run it only when all our parameters are up to 10 to the 10th. We'll run it 4 times, but it's fine. And there are like 100 tests. Should be very fast. I should probably run samples, right? My question been answered, yeah. It doesn't work. Interesting. That's a lot. Forgot the brackets here. Now it's working. Problem F. We have n distinct numbers, and quick glance input says that nothing else. We just have n distinct numbers. Only 3 chairs. If the heights of the lowest and the tallest of the united friends are not k-prime, then the friends will play tricks on each other. Yeah, that's how actual people behave. Don't write stories if they don't make sense. How many ways there are to choose 3 friends so that min and max are not k-prime? So we're actually like we can sort this thing, and we're choosing 2 numbers that will be min and max, and then just multiply by the distance. Well, okay. We should do exactly that. So sort our numbers. Then we want to calculate the sum over all pairs that are not k-prime. Distance between them -1. That's the number of ways to choose the third one in between. Okay, but then distance is like j minus I minus 1, and we can calculate the sum of j and the sum of I plus 1, for example, separately. So now, like, obviously those problems are kind of the same. So now we want to calculate the sum over all pairs of not k-prime numbers index of the second one. But then, obviously, if we fix the second one, we're only interested in number of ways to choose a not k-prime number before that. So we will do some kind of scan line, left to right. We will maintain something on numbers that we have already traced on prefix, and then like for each number we want to make a query. How many numbers not k-prime to this one we have already seen? This sounds like some simple inclusion-exclusion by users. Like, how do you calculate the number of numbers that are not k-prime to 6, for example? Well, you can take all numbers that are divisible by 2, they are not k-prime. You can also take numbers that are divisible by 3, they are also not k-prime. But that will mean that for numbers that are divisible by both 2 and 3, we have added them twice. We have calculated them twice. We have calculated them as numbers that are divisible by 2 and numbers that are divisible by 3. So we have to decrease it by 1 for each of them. So like subtract from answer the number of numbers that are divisible by 2 and 3 at the same time. But since 2 and 3 are k-prime, it's just the number of numbers that are divisible by 6. And so on. So what we will do is we'll pre-calculate all the divisors for all the numbers up to 300,000. And then calculate coefficients. Coefficients are actually Möbius function, whatever. Yeah, we will, when we encounter a new number, we first have to calculate the answer for it. This is done by using inclusion-exclusion. So we will sum like over all divisors that are greater than 1, number of already seen numbers with that are divisible by this number times its Möbius function times -1, I guess. And then we have to add it as already seen. We will run again through its divisors, and for each divisor just do ++. We have seen one more number with this divisor. That's it. Why is all distinct? Like, so that it works not in n times number of divisors, but like in sum of divisors, which is C log C. What's the point? Like, I think this solution still works if the numbers are not distinct. Boring problem. There are millions of the same problem. we do not consider 1 as a divisor, so let's just ignore it in precalc. Then we won't have to write ifs that ignore 1. Calculate Möbius function. We will calculate actually minus Möbius function, and it is done also by using inclusion-exclusion. We'll first initialize everything with 1, but then for each number that is divisible by it, we subtract the new function. Basically, like from this formula, we should see that like we are doing exactly what like inclusion-exclusion says to do. So that's how we calculate coefficients, then we just multiply by those coefficients. Nice fact that like all the values of Möbius function are either 0 or plus minus 1, and it is 0 exactly for numbers that are divisible by some square of prime, and for all others it is minus 1 in the power of number of different prime divisors. But here we multiplied by minus 1, and I didn't calculate in 1 because I don't need. So yeah. Normally I would say, like instead of this 4, I would say that mu of 1 is 1, and then just start it from 1, and that would calculate the correct values. Like first cycle would just set all the other mu to minus 1, and then everything is exactly like now, but multiplied by minus 1. Okay, I guess I'm ready. Ready to write the solution. So, as I said in the very beginning, we'll make 2 passes and independently solve for sum of j and sum of I. When we solve for sum of j, we are interested in the number of k-prime numbers on the prefix, and when we solve for I, we are interested in the number of k-primes on the suffix. So we will make passes in different order, but otherwise it's pretty much the same. And also in one of them I should account for that, like +1, -1. Also I need to clear CNT between 2 passes. I said that we should first calculate the answer, then change CNT, but since I will not use the same value of CNT twice, I can just change it right now after encountering it. So that's the first pass. I have calculated number of not k-prime numbers and then add to the answer that number multiplied by my index -1 to just accommodate that. And now in the other direction, this stays the same. I don't have 1 now, and I'm subtracting. If not k-prime, then bad. Okay, so we want k-prime actually. Okay, so we want k-prime, then we should include 1 and mus in the other, like multiplied by -1. I mean, not multiplied. Mine were multiplied. Incorrect. Interesting. Five is a lot. I'm not multiplying by now. Calculate, so I forgot to multiply. It's okay. I mean, it's not, but it's fixable. Come on. 0 is right, 77 is also right. Problem G, some strings. As you know, the dessert is a string of lowercase English letters. Tonya remembered the rule of desserts, a string S of length n. A string S is the rule, okay. Dessert T is delicious if the number of occurrences of T in S as a substring is divisible by the length of T. Tonya wants to know the number of delicious substrings of S. If the substring occurs several times in the string S, then all occurrences must be taken into account. What? In the first sample, no, I don't want the first sample, I want the sample. We have 5 different strings, substrings, just by letters. So since the answer is bigger than 5, it means that they should be counted the number of times they occur, and number of occurrences of string length 1 is 5. 5 is divisible by 1, so we add 5. 4 is divisible by 2, so we add 4. 3 is divisible by 3, so we add 3. And 2 is not divisible by 4, and 1 is not divisible by 5. So the answer should be 5 plus 4 plus 3, that's 12. That works. Okay. Why is it not like construct suffix out and on and that's it? Like, I can construct suffix out and on, for each node calculates the number of occurrences, and we have like a range of lengths for this node. So we need to calculate the number of divisors of this value in the given segment. You can't be fucking serious. So this problem is literally construct suffix automaton and do exactly what is written still. And they added divisors because they love divisors, I guess. Like problem F was about divisors. The round will be unrated. Made a mistake in problem C and can be solved with the given constraints. Fuck you guys. No comments. So this was divisors, this was divisors, this was divisors. Yeah. I mean, I like number theory. I don't like when all the problems are the same. And well, the problem about strings is it requires just direct usage of suffix structure. That's impressive. Like that's impressively bad. To the 6. Can I pre-calculate all the divisors to count? Or should we want something better than that? I guess I can do some shit offline. Right, like I will have some queries of form calculate the number of divisors on a segment. Then so that's like calculate the number of divisors on prefix. And then I can store all those queries, iterate over numbers from 1 to the 6, and like when I add new number, iterate over all the numbers that are divisible by x and increase counter by for them. Then answer all the queries for this prefix of numbers. Like for each number, I just store explicitly the number of divisors that are at most x. I just look at all the queries I want to answer now, and that's it. Then I don't need to do analog and pushbacks. Okay, cool. Let's implement some suffix automaton. Why not? There should be something educational. So what is the suffix automaton? What do we have in Node? We have transitions. We have suffix lin. And we have lens. In suffix automaton, there can be at most 2n nodes. And then from each node I will get two queries on prefix. So the number of queries will be the number of queries will be 4 times n, and I will need some something. Okay. Okay, I think that should be enough. We have a string, lens n. We have one node, root, and now starting root. Now we are adding symbols to suffix automaton. After create some copies. Yeah, I don't want to start here. So for each node, I will need to calculate the number of occurrences. So each time I add new symbol, I know the node that corresponds to this prefix, and I will say that this node has one more occurrence, and after that I can collect, push this up using suffix links. That will be correct. I don't want to do DFS, I don't want to store the graph. Instead, I can just write down all the vertices with their lengths and sort. I know that suffix link has smaller lengths, so if I will iterate over vertices in decreasing order of lengths, I will visit each node before I visit its suffix link. so I can push it there, like that. That's some order that is valid. So we are staying in this vertex. It has suffix link. That's why I'm not looking at the last vertex, because it is root. Let's assert that, why not? The last one is root. It has length 0 and ID 0. So the root doesn't have suffix link, so I will not push value from this vertex to its suffix link. But for all others, I should do that. Okay, now again, for all vertices except root, because it corresponds to empty string. So this vertex, its suffix link. And so I know the number of occurrences of all the strings that correspond to this node in suffix automaton. It's occurrences of v. And what are the lengths of the strings? Well, maximum length is stored in SA of v.len, and for smaller for lengths at most SA of u.len, we should go higher in the suffix link tree. So the corresponding lengths are SA of u.len not inclusive and SA of u.len inclusive. And like not inclusive, I want to take with minus sign. Inclusive, I want to take with plus sign. In the queries. So what do I need? I need up to which number I'm looking, and for which number I will look at the number of divisors. I also need the coefficient, but I can just multiply the number of recurrences by coefficient, because coefficient is always either 1 or minus 1. So okay, I'm just storing another bit in that number. So q of 2 plus plus a of u.len minus occurrences of v plus occurrences of v. Now I can sort all the queries I want to make, and I will do kind of two pointers. So first I increase the counter for all the numbers that are divisible by x. This works in n log n in total. And now I will look at all the queries for which I want to calculate the sum up to this number. So I want to answer what is the number of divisors that are at most x for this number. And so if it is less than 0, then I need variable for answer. It's ans minus equal cnt of minus qp second, because I want absolute value. Otherwise, ans plus equals cnt of qp second, p plus plus. And what's left is to implement the add function. Stay in vertex v, and I need to append symbol c. Create new vertex. This is just sample algorithm. If I will be talking what if I will be talking what it is doing, it will be harder for me to remember it, because I remember it like line by line. I understand what is going on, but there are a couple of ifs I have to not forget about. So I'll just do it without talking, and then I will go through the algorithm. So let's look at the the queries, which I need to multiply by the number of occurrences here because the statement says so. I don't understand why. I think it would be exactly the same problem. Eleven, 12. Interesting samples. Okay, so it works. Well, let's submit, and then if it gets accepted, then so suffix automaton. Each node, like it's kind of a try, but some nodes are compressed. Try like classic automaton, but some nodes are compressed if their the set of right ends of their occurrences is the same, and like we can show that their length will be a segment, and so len is max of those segments, and when we decrease the length, obviously all the occurrences that were will stay, but at some point there can be like new occurrence somewhere which like with bigger lengths it is not the same as it was before, and that will be like another node to which will point softLink. So softLink is a directed edge to the node that is like the largest our suffix, which has more occurrences than us. Yeah, and so like it can be proven that there will be linear number of nodes and edges, and we can construct it in like linear time times something to store the edges. Like we can either store edges in each node as like map from symbol to where we go, then it has lock overhead, or like I did here, we can just store an array, then we don't have any overhead like time-wise. So like this algorithm is kind of linear in time, but it takes n times size of alphabet memory, which is kind of weird. Like we need to initialize that memory somehow, but like initializing with zeros works. So well, I'm not sure exactly what will be going on here. So maybe when I like write this, it will call default constructor, and then it will fill it with zeros. But I guess if I don't call this default constructor and just say that don't write the default constructor and like softLink equal to -1 only needed for the root, so I just write it here, but like filling with zeros, I don't know how it is done, but like I know that the variables in global space will be filled with zeros. So I'm not sure that we actually spend like this n times alphabet time. I'm sure that we have n times alphabet memory, like here it is. Like, each of those things has an array inside, and it should all be on stack. So it shouldn't be like dynamically allocated. So all of this memory is used. It is accessible, but we don't actually do it. Like we only access linear number of cells in our memory. But like I digress. So like it can be proven that there is this automaton compressed with a linear number of nodes and edges, and it can be built using the sync, and it works in linear time in total. I don't know how to prove any of that. I just know like this code works for some reason. But like the idea of this code is the following. Well, I'm staying in this node now, and I want to add new symbol, so I create a new node. I know that like there wasn't any substrings of length of my new whole string before, because it was one simple shorter. So there should be a node that stores like the whole string, and this will be this node. So its length is my whole string, which is like my previous whole string plus 1. Okay? So now so we have created a new vertex u. That is on this edge is written the letter C. Now we look at our suffix links. Suffix links in the end they make a tree which is rooted in the root of our tree. Well, each node has a parent except for the root, and there are no cycles because we always decrease the length, so it should be clear that this tree, but like it's good to remember about that. And actually like this tree is the same tree as suffix tree for reverse string. Again, I don't really know why, but it is true and it can be used. Like for example, you can build suffix automaton for reverse string and get suffix tree for free. So we will go up, and for example, this node can either have an outgoing edge using symbol C or don't. If it doesn't have, then like what does it mean? I had a string. I wrote symbol C next to it. This substring corresponds to node V. Then if we try to look at its suffixes, at some point we will arrive at this node. That's like the definition of suffix link. Like for some length, that's the only right border of occurrence, and at some point we will arrive at some string which is occurred somewhere before, right? So these two are equal. And suppose it doesn't have an outgoing edge using letter C, but now I added C here, so there should be some node that corresponds to this string. And we know that like node U will correspond to the string which is like our whole string. And also it will correspond to some other strings like shorter lengths that has only one occurrence that ends at the end of our string. And I state that this is one of those strings. Yeah, that's right. This string is one of those strings. Why? Because, well, if it isn't, it is a suffix of our string. So if it isn't, if it should be stored in a different node, then it means that it should have had some other occurrence with C and Z. But if we cut out this C, then this string would be equal to this string, which corresponds to this node. And that means that after this string, we can write a symbol C and it still will be a substring. So there should be an outgoing edge using letter C. So this is not the case. So from this node, there now should be an outgoing edge with letter C that goes to a node that represents this string. But the string is represented by node U, so we create this edge. And we do it until we will find a node that already has an edge with outgoing C to some node. Let's look at the code. So I take the first sublink, and while well, I have not go outside of the tree, and I don't have outgoing edge using letter C, then I say that now I have, and it will go to vertex U, and then I go further up. At some point I will stop. I will either go out of the tree of my tree of suffix links, so like up to the root there was nothing, like no edges with letter C, and if that happened, that means that my letter C is the first letter C in the string. Otherwise, like there would be a node that corresponds to just substring of one letter C, and the edge from root to this node, root would have an edge with letter C. So if that didn't happen, that means that this letter C is the first one in the string, and where should our sublink point? Well, there is no other node that corresponds to a string that has letter C in the end. So we just point to root, and that's it. Our all of our structure is correct. Okay, now we are looking at the node. Like we have exited this cycle by the second condition. V is not -1, so this should become false. So we have arrived at some node that has an outgoing edge marked with letter C, and I called it X here. So this is node X. Okay, so this node was corresponding to some suffix of my old string, and it occurred somewhere before, such that we can write letter C and it still will be an occurrence, right? And this node X, it was corresponding to, among others, to this string. Okay. We should have a node that corresponds to the string, but maybe it was corresponding to other strings. What other strings? Well, maybe it corresponded to what? Well, it should have the same set of like red border occurrences, So we know that it corresponds to this string, but maybe it corresponded to like shorter strings that ends at C, or longer strings that end at C. No, that is wait. Yeah, fine. This is possible. And do we have such like longer strings that correspond to this node? Is determined by, well, length that is stored in that node. If it is equal to like this length, which is length of this node plus 1, plus symbol C, then we don't have such strings corresponding to that node X. And if it is strictly bigger, then we do. It cannot be strictly smaller because we know that this string corresponds to this node. And those two cases are different. Let's look at the code again. If we don't have, so the length of node X is the length of node W plus 1, then we will say that this node is just our suflink, and that's it. So like now we are trying to find suflink for our node, our new node, for this one. Like we say that all the edges are fine, which is not true, but for now let's say that, and we are trying to find where to put this suflink. So it kind of should go to this node, right? It's like the first time we encountered some suffix of us that we can put letter C next to. But that's actually not true, right? If we had longer strings, what does that mean? We know that this was the longest suffix of us to which we can put C in the end and get a substring that was that occurred before. So if we look at the longer suffix, then it doesn't occur there. So we know that like our previous symbol is not the same as previous symbol in this longer string. So it is not our suflink. Like it's not our proper suffix even. Like the longest string that corresponds to this node is not the suffix of this node. But like this string is, and it is also a proper suffix of this node. So what we will do instead, we will create a new node. That will only correspond to suffixes like starting from this length. This will be like new X, and we will say that suffix links from X and from U should go to this new node. And this new node, it is kind of similar to this one, and we just copy it there. But like right now, nobody goes to this node using actual edges in the suffix node. Like there are suffix links that point to this node, but there are no edges. But what can we like? We should fix that basically. And how we should fix it? Well, I say that for this node we should like instead of going to X, we should go to an X. Well, because reasons. I'm a bit tired to explain. Like I'm not very well versed. But not only for this, but basically all the nodes on this sublink path up that were going to x using symbol c now should go to nx, and like that's exactly what this code is doing. Like we create new node, we copy the contents of node x to nx, then say that its length is just length of previous +1, because all longer strings that corresponded to node x should stay in node x. Then we say that suffix links from x and u should now point to an x. And now we do a cycle similar to this one, but like while the edge marked with letter C goes to x, we should redirect it to nx actually and go up, and only then we return node u. So this suffix on it works. And the constant. Four and a half thousand idiots submitted some greedy. Good for them. Good for authors. No comments. Thanks for watching. Bye.